Hello. So we are now on part 4 of our discussion on finite projective planes. So far we have proven that all duals of the axioms of the finite projective planes are theorems. So they are already proven. So we can say this time that the finite projective planes is or does indeed satisfy the principle of duality. Let us now proceed to our fifth theorem. Theorem P.5. So this theorem states that in a projective plane of order n, each point is incident with exactly n plus 1 lines. Meaning, at every point, there are exactly n plus 1 lines passing through it. Okay, which is stricter than the preceding theorem. The preceding theorem asserts only the existence of at least one point where n plus 1 lines pass through. But this time it asserts that for every point on the plane, there should be exactly n plus 1 lines passing through it. Okay, so here is the proof. Let P be a point on the plane. Then, axiom P.2 would guarantee the existence of a line that contains exactly n plus 1 points, P sub 1, P sub 2, up to P sub n plus 1. But there could be two possibilities in this case. Either P is on that line L or P is not on that line L. Okay? Let us first take the second of the possibilities. Case 1 is where point P is not on that line L, as what is being shown in this figure here. So we have here the line L containing points P sub 1 up to P sub n plus 1. Wherein P is outside of line L. Okay. Now, in which case, by the proof that we have done in the preceding theorem, it can be proven that there would be exactly n plus 1 lines that would pass through P. Since that point in the preceding theorem also has the same condition as this. It is outside of the line with n plus 1 points. So again, P would have n plus 1, exactly n plus 1 lines passing through it. Okay, so let us now proceed to case 2. Case 2 is when the point P is one of those points on L. Okay, so as we can see here in the figure, so that this is the line L, which is said to have exactly n plus 1 points, and P happened to be one of those points. Without loss of generality, let us assume it to be P sub 1. Suppose P is that point on L, which is P sub 1. But then, axiom P.1 would guarantee the existence of a point not on L, because otherwise if all points are on L, then all points are collinear, it would not satisfy the first axiom. There should be, diba, again, sa first axiom, there should be at least 3 points non-collinear. Okay? There exist at least 4 points in which 3 are not collinear. So the points on the system cannot be all of this P sub 1 up to P sub n plus 1. There should be another point not on L. So let us call that point Q. Okay, now it can be verified that there should exist a line on the plane that do not contain P nor Q. So let's call that line M. The proof will be left as an activity. Okay, there exists a line which does not contain P nor Q. So M contains neither P nor Q. Now, it was proven that for a point not on the line containing n plus 1 points, L is that line, the line that contains n plus 1 point, and Q is not on L. So, it would follow from case 1 that there would be n plus 1 lines passing through Q. There are n plus 1 lines passing through Q. But each of those n plus 1 lines would be different from M because M does not contain Q. Okay, so there are n plus 1 lines here which is different from M. Then, axiom P.3 assures that for every two distinct lines, there is at least or exactly one point incident with them. Meaning, each of those n plus 1 lines must intersect M at some point. Therefore, but each of those points of intersection should be distinct. Otherwise, the lines passing through Q would not be distinct also. Meaning, M would have at least n plus 1 points on it with regards to or with reference to the n plus 1 lines passing through Q. So each of those lines would yield a unique point on M. So M would have at least n plus 1 points on it. And at the same time, there could be no more than n plus 1 points on M. Why? Because if there is another point here on M, it would follow that there would be another line that should connect Q and that point. Meaning there would be more than n plus 1 lines passing through Q. So this cannot happen because it is already proven that there is exactly m plus 1 lines through Q. So M therefore can not also have more than n plus 1 points, meaning M must contain exactly n plus 1 points. But take note, P, the point we have assumed earlier, is not on that line M. And line M contains exactly n plus 1 points. Meaning, with reference to case 1, P should be incident with n plus 1 lines also. So since P is now a point outside of a line M which contains n plus 1 points. Meaning P, which is on L that contains n plus 1 points, now has n plus 1 lines also incident with it. Okay, so from cases 1 and 2, we now have proven the theorem. That is theorem P.5. Let us now proceed to theorem P.6. Theorem P.6 states that in a projective plane of order n, each line is incident with exactly n plus 1 points. Now, the order n here is now being introduced. Order N here refers to that integer, positive integer, mentioned in axiom P.2 and the preceding theorem. Okay, so that is the reference for the number of points on each line and the number of lines on each point. So let us try to prove this. Each line is incident with exactly n plus 1 points. Now, meaning each line contains exactly n plus 1 points. So say let L be a line on a finite, let's call it FPP, finite projective plane of order n. But then, not all points cannot be on this line. Otherwise, all points would be collinear. So, by virtue of axiom P.1, there must be a point, let's say P, not incident with L. But by the preceding theorem, there should be n plus 1 lines incident with P. Exactly n plus 1 lines. N plus 1 distinct lines incident with P. Now, each of these n plus 1 lines should intersect line L by virtue of axiom P.3. Each of this n plus 1 lines must intersect. Let's just use the word, although we have not been, or such word has not been defined yet. So let us just take the word intersect to mean that lines have or lines are incident with at least one common point. And lines must intersect L. But the points on L let me make this smaller first. Okay, so let us refer to a figure. So we have a line. There should be a point P, not on this line. Then there are lines passing through P. So again, there are n plus 1 of them. Each of this line would intersect L. So again, this is L here. This is L. Each of these blue lines must intersect L at some point. Now, these points of intersection, the points on L, contained by the lines incident with P must be distinct. Why? Because if two of those points are one and the same, and both lines contain P, then the lines would be one and the same. Then there would be less than n plus 1 lines. Okay, so that is by virtue of axiom P.3. Meaning, L contains or is incident with L is incident with at least n plus 1 points. And there is at least n plus 1 points on L. Suppose there is another point. Q, or other than these n plus 1 points. There is another point Q on L. But by action P.3, there should be a line containing both P and Q. But Q is incident with exactly n plus 1 lines. Which means the line containing P and Q is one of those lines. Okay, that is so it is shown that there are n plus 1 lines passing through P. So L should contain at least n plus 1 points also. So let's call them P sub 1 up to P sub n plus 1. Now assume that there is another point here. Let's say Q. Q on L. Since P and Q are distinct points, then there would also be a line containing them. But all lines passing through P so P, this here is P. All lines passing through P has been accounted for, meaning that line that passes through Q and P is one of those lines. and Q is one of the points, the n plus 1 points. On L. Therefore, L is incident with exactly n plus 1 points, which proves the theorem. Next, okay, by the two previous theorems, it can be now proven that in a finite projective plane of order n, there are exactly n squared plus n plus 1 points and n squared plus n plus 1 lines. Okay, so actually the proof is there. Let us just illustrate that. Let P be a point on a finite projective plane of order n. So we have a point called P. P. Then every other point is on exactly one line joining it with point P. Every other point there are that is by P.3. Every two distinct points is contained by exactly one line, meaning each and every point would be contained by a line that passed through P. Okay, so all points here would be contained by a line passing through P. There cannot be any point on the plane which is not contained by a line that passes through P. But then, by theorem P.5, there are exactly n plus 1 lines passing through P. So there are n plus 1 lines passing through P. There. And by theorem P.6, each of these lines contains exactly n plus 1 points. So each of this has exactly n plus 1 points, meaning there would be n plus 1 lines or n lines n plus 1 lines, and each line has n plus 1 points, but P has been accounted for, so there are only n lines for each of these n plus 1 or n points for each of these n plus 1 lines that has not been counted yet, plus that of P, so plus 1. So this would be the total number of points. So there would be n squared plus n plus 1 points. on the plane. Then, since the system satisfies the principle of duality, then its dual would also be true. It could be verified, actually, that there are also n squared plus n plus 1 lines. Okay, actually the proof will just be the dual of the proof that we have done. We assume a line, then count the number of other lines on the plane. Okay, so I believe that would be that would be all of the topic. Are there no other theorems? Okay, so that is the last theorem for this lesson. It's now time for you to work on your learning tasks and activities. Let us go back to the module that I have provided you. So, activity 2. Given 2 points, you are to prove that given 2 points, there exists a line that contains neither of them. This is actually the part we have skipped in the proof of one of our theorems earlier. So, instead of me proving this conjecture, this statement, I would like you to make your own video showing your own proof of this statement and upload it to the internet and give me access to it so that I can see whether or not you got your proof correct before we discuss the proof together. Okay, so please again prove this statement. Record the process of making the proof. You can either show your face or not. You can just show your hand making the proof, but the voice should be there discussing the proof, and upload the video to our either the group chat, or you can send it to me through a personal message. Okay, we'll just discuss the proof for this statement as soon as I get all of your outputs, and then you do your second learning task. Thank you. So again, you might want to hit the subscribe and the notification button so that you would know when I upload a new video for our subject. That would be all, and good day.